Hi everyone. So from this video onwards, we are going to start studying about Maxwell's equation. But before studying Maxwell's equation, we need to know the meaning of some basic terms. So you might have studied these terms in your 12th class as well, but those who have forgot it or those who haven't studied it, for them we will study those basic terms. So let's start with some basic terms, which is volume charge density. So this we have already seen in one of the questions of vector calculus. What do you mean by volume charge density? That means charge per unit volume. So what is your volume charge density? Volume charge density can be defined by rho v, which is your charge per unit volume. Okay, volume I am showing by v, charge per unit volume. And from here, if I need to find the value of charge, how I can find it? dv goes here, and then both of the side I can do integration. Basically, this is what I am doing. dq equals to rho v dv, and both of the side I am doing the integration. Okay, so what I will get? Q equals to integration rho v dv. So this is how your charge is defined. This is your volume charge density, and this is how your charge is defined. So it is a vector quantity or scalar quantity? What do you think? This is scalar, this is scalar, this has to be scalar, right? This is scalar, so this has to be scalar only. So it is a scalar quantity. So better I should write in this manner only, scalar quantity. What I am talking about? I am talking about rho v. Rho v is a scalar quantity, right? Because this is also scalar and this is also scalar. Both are scalar. So it is a scalar quantity. It is of no use, no one will ask you this. Just you will need to know that Q is equals to integration rho v dv. This is the basic thing that you need to know. We have also solved a numerical based on this, right? What do you mean by current density? So current density are of two types. Current density are of two types. We will understand one by one. Surface current density and volume current density. And first we will study about volume current density, and this is a vector quantity. How it is vector, that we will see. So what do you mean by volume current density? So volume current density is amount of current flowing through per unit cross sectional area. So this is a cross sectional area. How much current is passing? That's it. So if I take a cross sectional area of 1 meter square, then how much current is passing from that? That is known as volume current density. So J equals to di by ds. So from here, if I need to find current, what that would be? That would be J into ds. Now why did I say that is a vector quantity? So let's just say this is my surface. So from here, how much current is passing? I current is passing. If I rotate this surface, then lesser current will pass. Initially, all these component of current would pass, right? It is same as flux. All these component of current would pass, but if I rotate it, if I start rotating it, so lesser current would pass, right? So that's why I equals to J dot ds. So these are just the basic terms we are studying. We are not studying Maxwell equation as of now. But if you don't know the meaning of these basic terms, then you would not be able to understand Maxwell equations. And if you are not able to understand Maxwell equation, then you will never understand EM wave. So we will study Maxwell equation in depth. What do you mean by surface current density? So for surface current density, I will take an example. So I hope you must have understood this volume current density. Okay, this volume current density is from the surface how much current is passing. Okay, now what is surface current density? Now let's just say this is something like this is kind of surface you are having. This kind of surface you are having, it has a width w. This line is w. It has a width w. I can show you the diagram on this page. So it has a width w. It has this width w, and it has this length. This length is very low. This length is very low. So if you see on top level, it would feel like that this is a simple wire type of thing. No, it would feel like it is a simple wire type of thing. What I am saying is that this is the width w, which is finite, but this length is very, very small. So it would feel like that it is a simple wire, but it is a surface. But in actual, it is a surface. Now from this surface, this I current is going out. You can see that is going out. Cross sign. Cross sign is it is going out like this. So it is going into the computer screen. Okay. So this I current is going out. Now tell me what I current is crossing. Which length I current is crossing? It is crossing this W length or it is crossing this small length? Cross. Basically, I current is going like this. This is how I current is going. So it is crossing the W length only, no? Look, it would feel, you will say that, sir, actually it is crossing the surface. Yeah, I know. The current is actually crossing the surface. The current is actually crossing the surface. But this width, I should say this length is very small. So it would feel like that it is a simple wire only. And it would feel like that the current is flowing through that wire. Or I should say the current is flowing through that line. So the current is crossing that line. If I make a surface, okay, and I am saying the current is flowing like this, then this is your current. Then what you would say, the current is crossing this line. The current is crossing this line. If I say current is flowing like this, then you would say the current is crossing this line. If I say the current is flowing like this, then current is crossing this line. And if I say current is flowing like this, then current is crossing this line. But if I say I am taking this kind of surface and current is flowing into this surface, current is flowing into this surface, so you would say that sir, current is crossing the surface. But the thing is, this is very small. If this is very small, that means it would feel like that it is crossing this width only. So what I would write? Di by dw. Okay, here I should not write the vector. So whatever the length it crosses, per unit length, how much current is passing? Basically, if I take a small length dw here, if I take a small length dw here, this is like taking a length only, because this would be very small. This would be very, very small. So if I take a small length dw, then how much current is crossing that? That is known as surface current density. Mark this thing, in volume current density you are having ds here, and in surface current density you are having dw here. Dw is like kind of dl only, it is a length. This is a surface area. In volume current density you are having surface area. In surface current density you are having a length. Okay, so what will be your current? Current will be k dot dw. This will also be a dot product. Now in the whole chapter, in the whole EMFT subject, we will be using these two terms again and again, static field and time varying field. What do you mean by static field? So any vector field, if this is not a function of time, if any vector field is not a function of time, that is known as static field. It should not be a function of time, or it's not necessary to be vector field, or we are going to study vector fields only, because both so let it be, if any vector field is not a function of time, that is known as static field. And if it is a function of time, it has to be a function of time, like there has to be time term, there has to be the term, there can be the term of space as well. In this let me tell you example. So some kind of field I am writing in this manner. How I wrote this, that is of no use, but just I am giving you an example. So here vector sign also come, ax cap, I am just giving you an example. So this is a function of time, so that is known as time varying field. So it is changing with respect to time. So time varying field means field changes with respect to time. What is the issue? Charger is on with respect to time. And static field means field is constant with respect to this field can change as per the coordinates, right? In x direction it could be something else, in y direction it could be something else, in z direction it could be something else, but it would not be a function of time. Is that clear to you? So now we are going to study about static field only. Okay, so we are going to study about electrostats and magnetostats. Now this is not a comprehensive course on electrostats and magnetostats, because that would take a lot of time and that is not even in your syllabus. So whatever that is required, that we are going to study. So what do you mean by electric field lines? So electric field lines are like a vector lines only. Electric field is a vector field only. Okay, electric field is a vector field. Okay, it is a vector quantity. So electric field is a vector field. Now if there is a positive charge q, so from the positive charge q, electric field lines will always go out. It will always go out. Electric field lines will always go out from a positive charge. And in the negative charge, electric fields will always come in. So what I would say, here the electric field lines are diverging, and here electric field lines are converging. Okay, so let me make them separate. Electric field lines diverges, and here I would say electric field lines converges. Now just for a fact, if I ask you, this is how I am showing electric field line, intensity of electric field line, this is how I am showing it. So just for the fact, if I ask you what will be your del dot E at this point P, what will be your del dot E at this point P? You cannot tell me the magnitude, but can you tell me the sign? What will be the sign of divergence? Positive, because electric field lines are going out. It is showing the outgoingness. And if I call this point as PQ, PR, so what will be the sign? Just the sign I am asking. That will be negative. Okay, just general knowledge it is. So you must have understood what do you mean by electric field lines. Now what do you mean by electric field intensity? So it is shown by E. So now from now onwards, whenever I write E, what you would say? It is electric field intensity. Now these are the electric field lines. Okay. Now in the electric field lines, you put a charge Q. In the electric field lines, these were my electric field lines. What did I do? I put a charge Q here. In my electric field lines, I put a charge Q. So this charge Q will feel a force, and that will be in the direction of electric field. It will feel a force that is given by Q into E. The force is given by Q into E. I hope you must have studied it. If you haven't studied it, then you can remember. In the presence of electric field lines, if you put a charge plus Q, that will feel a force in the direction of electric field lines. Now if it is minus Q, then what will be the direction of the force? In the presence of electric field lines, you are putting a charge which is minus Q. What will be the direction of force? If you just put minus here, then the direction will be opposite. So instead of showing Q, I am showing QE, capital QE here. So this Q could be positive as well, this Q could be negative as well. If it is positive, that means the force will be in the direction of electric field only. If it is negative, then the force will be in the opposite direction of electric field, right? Now from here, what do I get? F by Q, right? So what will be the definition of electric field intensity? That is not important. Only you need to understand one thing. What do you mean by electric field intensity? So whenever I say electric field intensity, in your mind it should struck that he is talking about E. That's it. Nothing else you want to understand. But just for the fact, what will be the definition? In the presence of electric field lines, the amount of force applied on 1 coulomb charge will be equal to electric field intensity. What is the name? Electric field intensity. This word is important. Intensity. Electric field intensity. In the presence of electric field lines on 1 coulomb charge, how much force is applied? That is equal to electric field intensity. Now, by a charge Q, what Q will do? It will generate some electric field lines. So how much electric field it will generate at point P, which is at R distance? What I am saying, by a charge Q, how much electric field will be generated which is at distance R from Q? So for that we have a formula which you do not need to remember, but I will be using it to prove something. Okay, I will be using this formula to prove something. So you do not need to remember this formula. Just you will see it and forget it. And if you already remember, then also it is fine. So that is given as KQ upon R square. And the direction will be along the line joining this point and this point. So this will be the direction. So direction will be this R cap. Okay. What will be the direction? Direction will be along the line joining plus Q and the point P. So this will be the formula of electric field. Even if you don't remember it, then also it is fine. Here what is K? K is a constant which is equals to 1 by 4 pi epsilon. Okay. We will talk about this epsilon. Epsilon is known as permittivity. Permittivity of the medium. Permittivity of the medium. So we will talk about it. Okay. Do not worry about it. We will talk about permittivity. Permittivity of a medium. So these are the basic 12th class things which we are studying. and these are important to prove some of the formulas to prove the Maxwell equation. Basically these are important to prove the Maxwell equations. That's why we are studying it. Well and good. Okay, now there is another term, electric flux density. I'm not going to tell the definition, because do you remember the definition of field flux density? Did we study it? Field flux density, flux per unit area. What was the flux density? What do you mean by flux density? Flux per unit area, that's it. This is the same thing here. Okay, so this is shown by D. Electric flux density is shown by D, which is equals to epsilon E. Okay, it is equals to epsilon E. Are you getting this point? D is epsilon E. This is what you need to remember. Anyway, you need to remember where E is the epsilon is the permittivity of the medium. Look, we are not going to study the complete electrostatic, right? So we cannot prove all these things. So some things you need to remember. Now this epsilon, okay, here only I will write about it. Yeah, now one more thing. Now this electric field E will depend on epsilon, right? Electric field E is a function of epsilon. Electric field E is a function of epsilon, right? Now tell me one thing, whether this D will be a function of epsilon or not. Think about it. Whether this D will be a function of epsilon or not. No. Why is that so? Because what is D? D is epsilon into electric field. What is electric field? One formula I know. I know one formula only. I know a formula because of the point charge only. If the charge is spread on a sheet, what will be the formula? That would be something else. So that we are not going to study, that electrical people will study. Whatever that is required, I don't even need to remember this formula. This is just for my reference, because a lot of things I will be deriving using this formula only. So that's why I am taking as a reference. So what do we get? D is equals to kq by r square. Kq by r square, where k is 1 upon 4 pi epsilon naught. Q by r square. Whatever the formula we will get, but epsilon and epsilon are getting cancelled. So D is not a function of epsilon. So your D will not depend on the medium, because permittivity is defined specifically for a medium. If it is a free space medium, or if it is a conductor, or if it is a dielectric, so for different mediums epsilon will be different. So epsilon is defined for the medium only. And now, so your electric flux density doesn't depend on medium. Can you remember this thing? Okay, very simple thing. Just you need to think that, okay, electric field is 1 by epsilon. Okay, so it is depending on epsilon, but electric flux density, your electric flux density, just a second. Yeah, so what I was saying, your electric flux density does not depend on the medium, but your electric field intensity depends on the medium. There are two terms, electric field intensity. Here the term is electric flux density. So D, if I say D, that means electric flux density. And if I say E, that means electric field intensity. So both are two different terms. Now let's talk about this epsilon. So this epsilon is given by epsilon naught epsilon r. Okay, where epsilon naught is known as absolute permittivity. Absolute permittivity. So as of now, you do not need to mug it up, because these things will be again and again used. So eventually you are going to remember it. Okay, so again and again it will be used, and this is epsilon r is known as relative permittivity. It might seem a bit boring to you. This lecture might be a bit boring, because we are not covering electrostatics in a comprehensive manner. If we cover it in a comprehensive manner, it would take around roughly 30 to 40 hours, and that time we cannot spend, right? Because that is not mentioned in our syllabus. But if you do not know the basics of electrostatics, then you would not be able to understand Maxwell equations. So that's why whatever that is required, that we are studying. Yeah. Now there is a certain value of epsilon naught, that is 8.85 into 10 to the power minus 12 farad per meter, or it can be equals to 1 by 36 pi 10 to the power minus 9 farad per meter. Unit is farad per meter. Okay, so this data might be given in the examination if they are asking a question, but you should remember it. at least this you should remember, that what is the value of epsilon naught. Okay, so this was your epsilon naught. Now this epsilon naught could be not talking about epsilon naught, talking about epsilon r. So epsilon r will always be greater than or equals to 1. Epsilon r will be always greater than or equals to 1. So which is known as relative permittivity. We will discuss about epsilon in a good manner as well when we study EM wave. So that will come again. Epsilon will come again. There we will discuss about it. There I will tell that this could be real as well. It could be complex as well. So the value of epsilon r could be complex as well. So that we are going to study when we study EM wave. Okay. So as of now, you just need to remember how much things you need to remember as of now. What is your electric field? If I say electric field intensity, that means I am talking about E. That's it. This is what you need to remember. If I say electric flux density, that means I am talking about D, and D is equals to epsilon E. Epsilon is equals to epsilon naught epsilon r. Epsilon naught is absolute permittivity, epsilon r is relative permittivity, and what is the value of epsilon naught? 8.85 into 10 to the power minus 12 farad per meter. So this is the summary of everything that we have studied till now. So this is what you remember. This is what you need to remember till now. Okay. Now let's study about electric flux. So have we studied about flux? What do you mean by flux? Number of field line crossing a particular surface area. Number of field lines crossing a particular surface area. So that was your electric flux. And how flux was defined? Flux was defined as, how flux was defined? Flux density dot surface area, and then the integration. Do you remember how flux was defined? Flux was defined flux density into surface area, because what was your flux density? Flux per unit area. So from here you could define the flux. So how electric flux will be defined? So electric flux will be given as, what it will be given as? D dot ds through a closed surface. Is that clear to you? This is how electric flux will be defined, and that is denoted by phi E. Phi E. Okay. So this is also you need to keep in mind. What will be my electric flux? D dot ds. Integration D dot ds. Now there is a law called Gauss law. I hope you must have studied it. So Gauss's law is there. What does it tell? So it tells that total electric flux through a closed surface, total electric flux through a closed surface is equals to the charge enclosed within the closed surface. Charge enclosed within the closed surface. So Q enclosed I am writing. So this is what Gauss's law says. Total electric flux through a closed surface is equals to the charge enclosed within that closed surface. So let's just say this is a spherical surface. This is a closed spherical surface. What do you think? What should I write here in Q enclosed? What should I write? Charge enclosed this surface. So charge has to be enclosed. So what I will write? Q1 plus Q4 minus Q3 minus Q2, Q5 and Q6 are of no use because they are not enclosed by the surface. So what I will write? Q1, Q2 is negative, so minus Q2, Q3 is also negative, so minus Q3 plus Q4 is positive. So this is how your flux is defined. Won't be that useful, it will not be that useful, but still you should know these much of basic things. Okay. Now let's see this question. So these kind of questions are asked in the examination. Oftenly these are asked. During my attempt in 2022 as well, these kind of questions are asked. So D is given. What is D? Here I did not write it, but in the examination it will be written. It is electric flux density. So D is written. D is given. You need to calculate the charge density at this point, and you need to find the total charge enclosed by the cylinder of 1 meter radius, and Z is going from minus 2 to 2. So it should be written clearly. Z is going from minus 2 to 2. So Z is from minus 2 to 2 and the radius is 1 meter. So total charge enclosed you need to find as well. So first thing you need to find charge density. So rho v you need to find. So what all I need to find? I need to find rho v and Q enclosed. So from Gauss law so this you need to remember. Okay, D dot ds Q1 Q2, this thing you need to remember. Wait a second. One more thing I wanted to tell here that I forgot. Yeah, so this is what you got here, right? D dot ds is q enclosed. Okay, so can I write it in this manner? D dot ds, if I apply the divergence theorem here, if I apply divergence theorem, what I will get? Say yes or no. Del dot d dot dv, this is what I will get. How I can write q enclosed? Rho v dv, right? First page. What is your q? Rho v dv. What is rho v here? What is rho v here? Volume charge density. Volume charge density. Per unit volume, how much charge is there? So rho v is volume charge density. Q I can write rho v dv, and this I can write del dot d dv. I hope you remember it. Del dot d dv. Dot is not required here. Del dot d dv. So dv dv is same. Sorry. What I am doing here, right? Basically, if you remember this thing, A dot ds was given by what? Del dot A dv. This was our divergence theorem. So this is how I can write it. So from here, what did you get to know? That my del dot d is equals to rho v. So very important, two results, very important. This result and this result. These two are very important. You need to remember it. Anyway, you need to remember it, because this is our first Maxwell equation. We will write it down. In the end, we will write it down. But this is our first Maxwell equation. So how will you remember? Okay, first thing, in the examination, directly you can write that, sir, d dot ds, this is our flux, which will be equals to q enclosed. So if I see this, sir, that I can write del dot d dv, and this I can write rho v dv. So del dot d is equals to rho v. What you will say, sir, flux is equals to q enclosed. So flux is d dot ds, and d dot ds is, sir, del dot dv, and this is, sir, rho v dv. So del dot d is equals to rho v. So this is what you need to remember. Okay, now d is given. You need to calculate the charge density, and also you need to calculate the total charge enclosed by the cylinder. So what all you need to find? Charge density rho v you need to find, and total charge enclosed by the cylinder. This is what you need to find. What this will be equals to? This will be equals to rho v dv. You can show 3 integration here as well, or I can show by 1 as well. Better, let's show by 3. So what is your rho v? Rho v is equals to del dot d, right? This is what I remember. Del dot d is equals to rho v. So what I need to find? Del dot d. So how will I find? What kind of coordinate system is that? Rho z cos phi. What kind of coordinate system is that? It is cylindrical coordinate system. So for that I am gonna write my del dot d. For that, what you will get? 1 by rho. I hope till now you must have remembered the formula. 1 by rho into whatever the expression here is, rho square z cos square phi. Rho square z cos square phi plus 1 by rho del by del phi. Sorry. Here 0 will come, no? Because that was AZ component. Sorry. Blunder from my side. Here also 0 will come. And here del by del z, this will come. Rho z cos square phi. Rho z cos square phi. Okay, here A rho component come, here A phi component come, here AZ component come. So only AZ component is mentioned here. So AZ component only will come. So this will be 0 only. So this will be 0 only. So this will be 0, this will be 0 only, this will come in action, which will be equals to rho cos square phi. This is your rho v. Now at a certain point they are asking, so what will be your rho v at 1 comma pi by 4 comma 3. 1 comma pi by 4 comma 3. So 1 comma cos square pi by 4, right? So this will be 1 by 2 coulomb per meter cube. Okay, this will be your rho v at a certain point. Now I need to find q enclosed. So for Q enclosed I need to write rho v, which is my, so Q enclosed they are not asking at a point, certainly they cannot ask at a point. So they are asking for like what will be the total charge enclosed within that volume of this cylinder. So 1 meter radius is there, value of rho will go from 0 to 1 and z will go from -2 to 2 and phi will go from 0 to 2 pi. I hope you must have solved these kind of problems and now it is very easy for you. And what will be your dV? dV will be rho d rho d phi dz. If you have studied the vector calculus part, then only you will be able to understand. You should have a good idea of coordinate geometry as well, vector calculus as well, then only you will be able to understand all these things, right? So what is the radius? Radius is 1 meter. So value of rho is going from 0 to 1 and value of z will go, phi value we can write, or z also you can write, but let's write down phi. So value of phi will go from 0 to 2 pi and value of z will go from -2 to 2, right? -2 to 2. Okay. So now rho term I will take one side. So what I will get? Rho square by 2 from 0 to 1. Cos square phi and limit is from 0 to 2 pi. What is the answer? Pi. I hope you remember it. 0 to n pi cos square phi d phi. What will be the answer? N pi by 2. So here 2 pi by 2, that will be pi. And z is going from -2 to 2. So only z term is dz only. So the integration will also be dz only. So -2 to 2. So what you are getting? 1 by 2 into pi into 4. So what is the answer? 2 pi Coulomb. Okay. No. Answer is incorrect. So let me check once. Yeah, so one blunder I did here, which is here it will be rho cube by 3, right? Rho squared, it would be rho squared d rho. So rho cube by 3 and rho is going from 0 to 1. So answer will be 4 pi by 3 Coulomb. Okay. So this is your Q enclosed, this is your other answer. So very easy question. First I calculated del dot D, which gave me rho v, and from rho v I could calculate Q enclosed, right? Let's go to the next concept. This is a concept only. So what they are saying in static field, what do I mean by static? That my electric field is not time varying. My electric field is not time varying. Nothing is time varying. All are static. Electric field is static. Electric field is not a function of time. Neither if there is magnetic field as well, so that is also not a function of time. So in static fields, static field means either electric field or magnetic field or any kind of field, no field is a function of time. So in static field, del cross E is equals to 0, you need to prove it. So do you remember any formula of E? Yes, kq by r square ar cap I can write. kq by r square ar cap or r cap I can write. So can I calculate del cross E? Yes, certainly you can calculate del cross E. What answer you will get? So del cross E. So this derivation you do not need to remember, although it is a very easy derivation. So dr r d theta r sin theta d phi del by del r del by del theta del by del phi. Here what will come? Here kq by r square will come, and there are no component of a theta or a phi, so 0 0, and here outside 1 by r square sin theta, although it would be r into 0, it would be r into sin theta into 0, but it will be 0 only. So both will be 0 only. Now I need to solve this determinant. So what you are gonna get? 0. You can solve it. Ar cap would come 0 0. R a theta cap would come 0 0. R sin theta a phi cap would come then 0 0. So what is the answer? 0. So what did you get to know here? Del cross E is equals to 0. So from here, if del cross E is 0, then what you can say? That my closed line integration of electrostatic field. What I am saying? Electrostatic field. So closed line integration of my static field along any path is equals to 0. And what all conclusion I can make from it? This we have already studied, right? If del cross E is 0, then closed line integration of this field will be 0. And from here what you can say, that electrostatic fields are conservative in nature. Electrostatic fields are conservative in nature. So what did you prove here? Look, this is not the correct proof actually. To be very honest, this is not how this should be proved. It should be proved that I will take electric field, okay, then I will move from here to here, A to B, okay, then I will move from B to E, B to A, and then I would find the E dot dl value. That would come out to be 0 as well. This is how it should be proved ideally. But there is nothing wrong in this proof as well. And this is no one is going to ask you. That's why I just proved it that del cross E is equals to 0. If your del cross E is equals to 0, then your closed line integration of electric field, electrostatic field, I should not say electric field, electrostatic field, closed line integration of electrostatic field is 0. And if electrostatic field, closed line integration of electrostatic field is 0, that means electrostatic fields are conservative in nature. So what you will say, electric field are conservative in nature? No, electrostatic field are conservative in nature. Because when we study about time varying field, then you would see that this formula will change. Okay, so this is our second Maxwell equation where we get to know that your del cross E is equals to 0. But this is always not true. Okay, always not true. True for static field only. True for static fields only. This is a very, very important point. Okay, now let's revisit our null identities. What do you remember? Your CG is 0. Your CG is very low, so CG is equals to 0. And what do you remember by CG equals to 0? The curl of any gradient is 0. So curl of any gradient is 0. Now what did I get to know? That my curl of electric field is 0. Again I am saying it wrong. Curl of electrostatic field is 0. What did I get to know? That curl of electrostatic field is 0. So that means the electric field can be written as the gradient of some other scalar field. Again I am repeating. Curl of gradient is 0. Then I got to know that curl of electric field is 0. That means electric field can be written as the gradient of some scalar field. Is that clear to you? And that scalar field is known as potential. And electric field is equal to the negative gradient of the potential. Okay, so this is what we are going to write next. So what do we know is that my curl of gradient is 0. That means del cross del f is equal to 0. That means this is what I have told. So what does that mean? That if my curl of any vector A is 0, that means that vector can be written as the gradient of some other scalar field. A is gradient of f of scalar field f. So similarly from here what I would write, the electric field is negative gradient of electric potential. So this V is known as electric potential. And what does this negative sign show? What does this negative sign shows? So this negative sign shows that in the direction where potential is increasing, the electric field will decrease. The negative sign shows that the direction of electric field is opposite in which, okay, did I say electric field will decrease? No, the direction of electric field will be opposite. In the direction where potential increases, the direction of electric field will be opposite to that. We will see an example, it will be more clear to you. We will see a numerical example. Okay. So first find the correct statement. Electric field are conservative in nature? No. Electrostatic field are conservative in nature. So let's solve this numerical now. So you need to find the expression of electric field intensity. The expression of electric potential is given to you. This is your electric potential. You need to find the expression of electric field intensity. So this thing we are going to prove. What this thing is saying? This thing is saying that the direction of electric field will always be in the decreasing direction of electric potential. Or I can say in the direction where electric potential increases, the direction of electric field will be opposite. Did you understand this point? Let's understand it more with respect to this question. So what we need to find? Electric field, which is equals to the negative gradient of V, right? So first we need to find the gradient. So r comma theta comma phi. So this is in spherical coordinate system. So dr r d theta r sin theta d phi. So I need to write down the gradient. So gradient is pretty easy. So I am writing del dot v. So del dot v will be what? D by dr, this expression, tan by r square sin theta cos phi ar cap. Then what I am write? I am not writing electric field. I am not writing electric field. I am writing gradient v. Okay, that's why I am putting the positive sign here. So that would be 1 by r d theta, 1 by r d by d theta, tan by r square sin theta cos phi ar cap, sorry, not ar cap, a theta cap, plus 1 by r sin theta d by d phi tan by r square sin theta cos phi a phi cap. Well and good. Now what will be the expression here? Now I am writing the expression of electric field now, which is equals to negative of this. So whatever the answer you are getting, you will take the negative of that. So what answer you will get here? 20 by r cube. But negative sign you will get, because r to the power minus 2 will go upward. So negative sign you will get, so that become positive. So sin theta cos phi ar cap plus 1 by r is there already. So tan by r square will come common, and differentiation of sin theta will be cos theta. So you are going to get, here you will get negative sign, because it is all positive. So you will get negative sign here. So minus 10 by r cube, minus 10 by r cube sin theta cos phi a theta cap, and here what you are going to get? What is the differentiation of cos phi? Differentiation of cos phi is minus sin phi. So one minus sign is coming because of this, another minus sign is coming because of this. So this will become positive. One minus sign is coming because of cos phi, and one minus sign is this. So it will become positive. So tan by r square sin theta, and then sin theta will also come outward. So that will get cancelled only. So this sin theta will come outward. So this will get cancelled. So tan by r square, and differentiation of cos phi is sin phi a phi cap. So this final answer is not important. What I want to tell you with this question, that is important. So what I want to tell you. So let me know one thing. In the direction of r, in the direction of ar cap, r increases. Like if I define, this is my ar cap, this is my a phi cap, and this is my a theta cap, whatever the direction I define. Okay, any direction I am defining. This is my ar cap, this is my a phi cap, and this is my a theta cap. Any random direction I am defining. Okay, overall perpendicular to each other. This is what you need to assume. So what does that mean? That in the direction of ar cap, the r will increase. In the direction of a phi cap, phi will increase. In the direction of theta, in the direction of a theta, theta will increase. You remember this, right? In the direction of theta, a theta will increase. In the direction of r, ar will increase. In the direction of phi, a phi will increase. Now if I increase the value of r, if I increase r, what will happen? V will go down. And what will be the direction of electric field? The direction of electric field will be in the same direction where electric potential decreases. Again I am repeating, the direction of electric field is same as in the direction where your electric potential decreases. So my electric potential, if I am going in ar cap direction, that means I am increasing the value of r. If I am increasing the value of r, then my electric potential is decreasing. So in the direction of ar cap, my electric potential decreases. That means my direction of electric field because of r will be in the direction of ar cap. So in the final answer you will get plus ar cap. Is that what you are getting? Yes. Again think about it. Again I am repeating the statement. What I am saying is that the direction of electric field will be in the direction where electric potential decreases. Now if I increase the value of r, that means increasing the value of r means I am going in the direction AR cap. So if I am going in the direction AR cap, then my electric potential is decreasing. That means the direction of electric field with respect to AR cap will be plus AR cap. Say yes or no? Yes, you are getting the same thing here. Now, if you increase theta, if theta is 0 degree, then what will be your V? 0 only. If theta is 45 degree, then your V will be 10 by r square 1 by root 2 cos phi. So if you increase theta, the value of sin theta will increase. If you increase theta, the value of sin theta will increase. If the value of sin theta increases, then the value of electric potential increases. So if you are increasing the value of theta, that means you are going in the direction of A theta cap. If you are going in the direction of A theta cap, then your electric potential is increasing. That means the direction of electric field will be opposite to A theta cap. So that means the direction you are going to get minus A theta cap. Is that what you are getting? Yes. Are you understanding this point? If you are not understanding, then go back to the video and again see it. Then you will understand. Now, let's take the third example. If I increase the phi, if phi value increases, then the value of cos phi will decrease. If phi increases, the value of cos phi will decrease. You can see the graph as well. So if phi increases, the value of cos phi decreases. If value of cos phi decreases, that means electric potential is decreasing. So if I am going in the direction of phi, then my electric potential is decreasing. If I am going in the direction of phi, then my electric potential is decreasing. If my electric potential is decreasing, then the direction of electric field will be in A phi only. So are you getting plus A phi? Yes. Is that clear to you? This is the meaning of electric field is negative gradient of phi. Okay. Where R increases, your V is going down. That means plus AR cap. Where theta increases, your V is going up. That means minus A theta cap. Where phi increases, your V is going down. That means plus A phi cap. So in a good interview, these kind of questions can be coming in your way. Okay. That what is the meaning of that negative sign? So that was important for interview perspective, not for the gate examination, but for interview perspective, these kind of things are important. If you say EMFT is one of your favorite subjects, so in these kind of things they can ask in Maxwell equation as well. Okay. So they will give this expression and then they can ask you electric field at a certain point. They will mention that point and then they can ask the expression as well. So very simple question that would be, right? So what is the summary of electrostat? This is a summary of electrostat. We are going to study magnetistat in the second half of this video. In the second half of this video, we are going to study magnetistat. So what is the summary till now? Del dot D is equals to rho V. So what was this? This was your Gauss law. How will you remember it? So what you will remember? That sir, one thing I know that whatever the total flux is, that is equals to Q enclosed. So what will be the total flux? Flux density dot ds, and that will be equals to Q enclosed. And how I can write it? Del dot dV. And how I can write it? Rho V dV. So from there I get this. Del dot D is equals to rho V. Eventually people will remember this formula, but they will forget this. So how will you remember this? That I have told. Flux is equals to Q enclosed. So what is flux? D dot ds. And then D can be replaced with epsilon E. But what did I tell you? Do you remember this thing? Do you remember this formula? In the last lecture only, or in the second last lecture we studied it. This F you cannot take outward. Directly you cannot take out. This F you can only take out if it is not a function of x, y, z, rho, phi, z or r or theta also you can say. So if it is not a function of space, if this F is not a function of space, then only you can take it out. Otherwise you will have to apply the formula. What was the formula? F as it is del dot A, and then A as it is del F, and then in between there is a dot. So this was the formula. I hope you remember it. We are going to use it somewhere. Okay. So that's why I wrote that formula. So epsilon you can take only out if epsilon is not a function of f y, x, y, z, r, theta, phi or rho. That means if epsilon is not a function of your coordinates, okay, then you can take it out. And if you take it out, then what will be the expression? Del dot E will be equals to rho V by epsilon. But you always remember the condition, because I am pretty hopeful that in the examination they are going to give something like that, that E will also be a function of space and epsilon will also be a function of space, and then they can ask you the value of rho V. So there you will be getting confused. Okay. So these kind of things can be asked. So Always remember this condition, and del dot D is equals to rho V. This also you should remember. And considering electrostatic field, your del cross E is equals to 0, or what you can write, the closed line integration E dot dl is equals to 0. What does it show? Conservative nature of electrostatic field. And what does it show? Del cross E is 0. If del cross E is 0, if curl is 0, then what do we call it? Irrotational, right? Irrotational nature. So electric field are irrotational in nature, electric field are conservative in nature. These kind of questions can come in MSQ. Not electric field, electrostatic field. Again and again I am also doing this mistake. So whenever you say electrostatic field are conservative in nature, very important thing. Electrostatic fields are conservative in nature and they are irrotational in nature. So this is the summary of whatever that we have studied. If you just remember this thing only, then you will be able to solve every single question that is coming in your examination. So whatever the time we have spent roughly around 40 to 45 minutes. In those 45 minutes, you only need to remember these things. So just revise these things, and you should know from where the formulas are coming, because if you know the derivation of formula from where it is coming, then you would be more comfortable in your examination. So in the second half, we are going to study about magnostat. So that will be completed in a very easy manner, and in a very brief manner it will be completed. So there also we will see two kind of outputs. So this is one of the output, del dot D is equals to rho V, and this is our second output, that is del cross E is equals to 0, and this is the integral form. This also is one of our outputs. So these kind of two output also we will see there. Okay, so that we will study in the second half of the video. I will pause the video, drink some water, you can also do the same, and then we will study the second half. So now we are going to study about magnostats. So we have studied about electrostats in our first half of this video. Now we are going to study magnostats. So first we studied about electric field lines. So what we studied, like there will be a charge Q, there will be minus charge Q, so they will generate electric field lines. This will diverge it, this will converge it. So this we have studied, right? Now here, how we will generate magnetic field lines? So we are having a magnet bar. You must have seen a magnet, right? So that is a magnet bar. So this magnet will have one north pole, one south pole. So this is having north pole, south pole. This is a magnet bar. So outside the magnet, the magnetic field lines will get out of the north pole and will get into the south pole. Outside the magnet, the magnetic field lines will get out of the north pole and will get into the south pole. Okay. So this is what I am showing, will get out of the north pole and will get into the south pole. And inside the magnet bar, the electric field lines will go from south to north pole. Inside the magnet bar, electric field lines will go from south to north pole. So outside north to south, inside south to north. Okay, you don't need to mug it up, just if you are able to remember it, then it is good. I just wanted to show this is your magnetic field lines. A current carrying conducting wire can also generate magnetic field. A current carrying wire can also generate a magnetic field. How it will generate a magnetic field? So this is my wire. So this is the current it is carrying. It is carrying current from down to up. So what will be the direction of magnetic field? Use your right hand. So this is the direction of current. My thumb is showing the direction of current, and in the direction where my fingers are rotating, my fingers are rotating in this direction, so that will be the direction of a magnetic field. So the direction of current is upward, my fingers are rotating like this, so that will be the direction of magnetic field. Okay, so this will be the direction of magnetic field. Okay, now if I ask you, at this point, this is the point which is parallel to this line, like this is my wire, and at this point what will be the direction? This is my wire. Okay, this is my wire, And at this point, what will be the direction of the magnetic field? I am asking, this is my wire at this point, the point is parallel to the line, completely parallel to the line. Here, what will be the direction? So this is the current, this is the current, this is the direction of magnetic field. So direction of magnetic field is going into the plane, right? Cross. And if I ask at this point, then magnetic field is coming out of the plane. Basically, you need to take tangent here. The direction is this, the direction is this, and the direction is here is this. So it is feeling like that the magnetic field is going into the plane. So that I am showing by cross, and this I am showing by dot. At this side, it feels like that it is coming out of the plane. So that is dot. Now, in the closed loop, if current is flowing, then what will be the direction of magnetic field? So current is flowing like this. My thumb will show the direction of magnetic field. So this will be the direction of magnetic field, which will be dot. Is that clear to you? This was my current carrying wire. So what is the direction of magnetic field at this point going into? And what is the direction of magnetic field here? So this is how my hands are rotating, no? So at this point it is coming towards me, and at this point it is going in. So you can see I am just drawing a tangent towards me and going out. And here, this is the loop which is having some current. This loop is having current I. Now because of this loop, what will be the direction? So this will be the direction. You don't need to remember it. It will be used nowhere. Just you need to understand what do you mean by magnetic field. If I say magnetic field, then what should come into your mind? So that only you need to remember. Now what do you mean by magnetic field intensity? So in electrostat, what we studied? Electric field intensity. In electrostats, we studied electric field intensity. Now we are going to study magnetic field intensity, that is shown by H. And electric field intensity was shown by E. So kind of I am relating them. Okay, I am not saying they are equivalent. I am just relating them, that electric field intensity and magnetic field intensity. So just one formula I will write down. You don't need to remember it. I just want to show something by that formula. So that's why I am writing it down. So do not remember it. Do not try to remember. So at this point, the magnetic field will be inside the plane, right? So what will be the intensity of magnetic field at a distance r? This is the same thing we are doing. At a distance r, what will be the intensity of magnetic field? So what will be magnetic field intensity? So you don't need to remember the formula. The formula will be H is equals to I upon 2 pi r. Now why I am writing the formula? Direction is going inward. Okay, this is how I am showing it. So why I am writing this formula? I want to show something. Okay, I want to show the dependency of medium. Here, why did I wrote the formula? Here, why did I write the formula? To show the dependency on medium. That electric field was depending on the medium, and here electric field intensity was depending on the medium, but electric flux density was not depending on the medium. So same thing I am going to show here. So here, is there anything which will show about the medium? I is the current, r is the distance, 2 pi is constant. So is there anything which is showing something of medium? No. So magnetic field intensity does not depend on the medium. So that we will write down later on. So first let's talk about magnetic flux density. So what was your electric flux density? D. That was equals to epsilon E. So similarly, my magnetic flux density will be equals to mu H. So whenever I say magnetic field intensity, H should come in your mind. Whenever I say magnetic flux density, then B should come in your mind. Okay, where what is mu? Mu is known as permeability. So we are going to write it down here only. Okay, now let's talk about that. Now what is mu? Here I will write down permeability. Now I will talk about that medium thing. So it will depend on medium or not. So this mu, that is known as permeability, that is depending on medium. So with respect to different medium, this mu is different. So mu is permeability of a medium. Okay, mu is the permeability of a medium. Okay, yeah. So now tell me one thing. So is that a function of mu, or H is a function of mu? Who is a function of mu? H is not a function of mu, because here you can say there is no formula of mu, there is no use of mu. But B is a function of mu. Okay, B is a function of mu. H is not a function of mu. So in that case it was opposite. D was not a function of D was not a function of epsilon and E was the function of epsilon. Okay, it is kind of irrelevant for you, but you should know these kind of things. So why I told this thing is that in 12th class you must have studied E and B, right? In 12th class you must have studied E and B, and in 12th class why did not we study D and H? In 10th class we study E and B because they are measurable. Why they are measurable? Because they depend on the medium. They are measurable because they depend on the medium. This is not even depending on the medium, so how will I measure it? So that's why we studied electric flux density and electric field intensity. In 12th class we call it electric field only, but that was wrong. In 12th class we used to call it magnetic field, which was wrong. It should be called as electric flux density. And this we studied, this was electric field intensity only. So this was correct, but in 12th class we used to call it magnetic field intensity, which was wrong. Magnetic field intensity is this, but since it is not depending on medium, it is not measurable. So if it is not measurable, that's why it was taught in our 12th class. But now we are going to study about H and E. Majorly we are going to study about H and E, but certainly B and D will also come in action sometimes. Is that clear to you? That's why I told this point. It will not be asked in the examination, but some guys will be getting confused that in 12th class we studied this thing, now we are studying something else. So that is the reason why they were calling it magnetic field intensity, but it is magnetic flux intensity. Sorry, magnetic flux density. Okay, so you should not be getting confused. Now, what is mu? Mu is equals to mu naught mu r, where your mu naught is absolute permeability and mu r is relative permeability. Mu r will always be greater than or equals to 1, and the value of mu naught is fixed, which is 4 pi into 10 to the power minus 7 Henry per meter. What was the unit of epsilon? Farad per meter. The unit of this is Henry per meter. Okay. Well and good. It cannot be complex. Did I tell epsilon r could be complex? Yeah, I told it. We will discuss about it later on, but it cannot be complex. Mu r cannot be complex. Okay, it can always be real. Hypothetically, in some question they can make it complex, but practically it will never be complex. So all these things we will discuss. Do not worry about that. Yeah. So in this slide, what you need to remember, that if I say magnetic field intensity, that means I am talking about H. That's it. And H is not depending on the medium. If I say magnetic flux density, that means I am talking about B. And B depends on the medium. If you want to remember dependency on medium, then you can remember, otherwise you can forget it as well. So till this slide, this is the thing you need to know, and then you need to know B is equals to mu H, where mu is equals to mu naught mu r. Mu is known as permeability, and mu naught is absolute permeability, mu r is relative permeability. What is the value of mu naught? That is 4 pi into 10 to the power minus 7 Henry per meter. Okay. Here I am not writing what does permeability show. So all these things are not important for you. We are going to study EM wave. That is the important part. Okay. We are not studying here electrostats and magnetostats. If you were studying electrostats and magnetostats, I would have told you what is the actual meaning of permeability, what does flux density is showing here, what is magnetic flux density, what are the magnetic field intensity by different kind of wires, all kind of things. So that we would have studied if we are studying what electrostats and magnetostats in comprehensive manner. But here we need to study Maxwell equation only. Okay. So electrical guys would be studying that, but EC guys do not need to study. So whatever that I am telling, only those things you need to remember. That's it. Okay. Now let's talk about magnetic flux. So what will be a magnetic flux? Magnetic flux density into ds. What was your electric flux? Electric flux was d dot ds, and that was equals to rho v. Sorry, q enclosed. Really sorry. It was equals to q enclosed. Okay. Now can I write it down in this manner? Del dot b dv dot is not required. Certainly I can write down, right? What I am applying? Divergence theorem. B dot ds, so del dot b dv. Well and good. Now let's just say this is a bar magnet. From this bar magnet, these are the magnetic field lines. So this is what magnetic field lines. So in the previous page I will show, this is your magnetic field lines. Now here I take a small surface. So this is the small surface I am taking. This is the small surface I am taking. Now from this small surface, magnetic field is getting in. As many magnetic fields are getting in, the same magnetic fields are getting out. If two magnetic fields are getting in, the same magnetic fields are getting out. Do you remember the concept of divergence? What is the divergence at this point? 0. Because what did I tell you? Think it as a water source. So whatever the water it is taking, the same water it is giving out. That means divergence is 0. If I take this field, if I take this surface area, or if I take any point here, so whatever the field lines are coming, the same field lines are going out. If I take any point here, any point here, let's just say any point I am taking here. So whatever the field lines are coming, the same are going out. Any point here I also I can take, whatever it is coming, the same are going out. Any point here also I can take, whatever that is coming, same are going out. So what did you understand by that? The divergence of B is equals to 0. Divergence of B is equals to 0. Or you can say B dot ds is equals to 0. This is known as, there are multiple names, okay, there are multiple names, what I will call it. This is known as Gauss law for magnetostats. The previous one is known as Gauss law for electrostats. So this is known as Gauss law for magnetostats. This is one of the name. What could be the other name? The other name is, it shows the inavailability I should write, or what should I write? Shows the shows the magnetic monopoles doesn't exist. What do you mean by that? So it cannot happen that only north pole is exiting. This will never happen. If there is a magnet, certainly if there is north pole, then certainly there will be south pole as well. Let's just say if only north pole was available, only north pole was available, okay, only north pole is there, no south pole is there. So what would happen? From north pole, electric field lines will go out, magnetic field lines will go out, right? Then you could say that, sir, at this point only the field lines are going out, nothing is coming in. Here at this point you would say that from south pole field lines are coming in, no, and going out as well. That's why here divergence is 0. But if only monopole is existing, then only it will go out. Or if only south is existing, that means only it will come in. So there you could say that, sir, divergence is 0. So divergence is non-zero. Here it is positive, here it is negative. This is what you would have said. But it never exists. Magnetic monopoles. Monopole means only one pole, either north pole or south pole. But if they are existing, that means certainly north pole and south pole will exist together. So whatever that goes out from here, the same will go in as well. So this is also, it is called. Or what else we can say? What else we can say? Whenever your divergence is 0, what will you call it? Whenever your divergence is 0, what you call it? Divergence-less or solenoidal. So magnetic field are solenoidal. Magnetic fields are solenoidal in nature. Okay, so these are the three things we can call. Gauss law for magnetostats shows the magnetic magnetic monopole does not exist. Shows that magnetic monopole does not exist, and magnetic fields are solenoidal in nature. Okay, now let's find out the curl. So for finding out the curl, we have a law which is known as Ampere's law. So you need to remember the name, Ampere's law. So what Ampere's law says that the closed line integration of magnetic field intensity H around a closed line or around a loop is equals to the current enclosed by the line. What it is saying, the closed line integration of magnetic field, intensity around a closed loop, or closed line is equals to the I enclosed within that loop, is equals to the I enclosed by the line. I enclosed by the closed line. Not only line, I enclosed by the closed line, or you can say loop. So here if I want to apply Ampere's law, what I would say, from this is not magnetic field, okay, don't think that I am making any magnetic field. No, I am taking a random closed line here. I just have taken a circular loop here. So I am taking a random closed line here. Okay, so what will be the closed line integration of H dot dl will be equals to the I enclosed within the loop. Okay, so this is your Ampere's law, which you should remember. So H dot dl is equals to I enclosed. So repeat it twice or thrice, this we have to remember. H dot dl is equals to I enclosed. There is no alternate way, this we have to remember only. Okay, now let's write down, let's try writing down its which form, divergence or curl, whatever we can get. So H dot dl, if I apply Stokes theorem here, what I am gonna get? Del cross H dot ds. Say yes or no. And can I write I enclosed that as J dot ds? And instead of J I am writing Jc. So where, what is Jc? Jc is conduction current density. Actually it is volume current density, conduction volume current density I should have said, conduction volume current density. But if they are not mentioning any volume current density or surface current density, by default you will take volume current density. So what was your I? I was, sorry, what was your conduction, what was your current density? What do you mean by conduction? That I will tell. Okay, do not worry about that. So di by dA, it was your di by dA. So what do you mean by conduction current density here? The normal current that we study. Let's just say this is a resistance. If I current is flowing, that is known as conduction current. But there will be one more current term that would be coming, that is known as displacement current. So in capacitor, ideally no current should flow, right? Through the capacitor, here in between the capacitor there is air. So if there is air, that means there should be no current flow. But still there is some current flow, that is known as displacement current. So that's why I have given a different name. So conduction current is a normal current. In any conductor, whatever the current flows, in a resistor, whatever the current is flowing, that is known as conduction current, which is a normal current. This I current is only conduction current. But why I have given the different name? Because displacement current will come in action in the next lecture. So that's why I am giving a different name. Okay. So Jc is the conduction current density, or I should say conduction volume current density. But if they are not mentioning it, then you will take by default what you will take? You will take only volume current density only. If they are mentioning about surface current density, then by default they will tell it. Okay. Or how I can say is that this closed line will enclose a surface, right? This closed line will enclose some surface, right? It will enclose some surface. So this current is flowing through this surface, and if the current is flowing through a surface, so what is that known as? Volume current density. And if the current flows through a line dw, that is known as surface current density, and this is known as volume current density. Okay. If the current is flowing through a surface, that is known as volume current density, and if the current is flowing through a line, that is known as surface current density. Well and good. So that's why di by ds, so Jc into ds. So from here what did you get to know? That your del cross H is equals to Gc. So this is also one of the Maxwell equation, and what you will call it? Ampere's law. What you will call it? Ampere's law. Okay. So let's see the summary. Del dot B is equals to 0. That means it shows the non-existence of monopoles, or what you can say, magnetic fields are magnetic fields are what? Magnetic fields are solenoidal in nature. Solenoidal in nature. And this is del cross S is equals to Jc, and B dot ds is equals to 0, H dot dl is equals to I enclosed. This was what was this? This was your Ampere's law. This was also your Ampere's law only. And this is Gauss law, you can say, or the same thing is there. Okay. this has the same thing. Is that clear to you? This is the summary. It was very easy. Magnetic field was very easy. So this is only the things that you need to remember. Nothing else. You can forget everything. Rest what you can remember is that B is equals to mu h. Okay. This also you should keep in mind. That would be it for you. Well and good. Okay. Now the conclusion of everything that we have studied, electrostats and magnetostats. So that is known as Maxwell equation. So Maxwell equations for static, electric and magnetic fields. So only static fields we are talking about. Here the fields are static. Okay. Fields are static. Nothing moved here. Electric field did not move and magnetic field did not move. Electric field and magnetic field both are not a function of time. Whenever they become a function of time, the formulas will be different. Did you see anything d by dt here? Anywhere did you see d by dt here? No. Del cross h. So del is a d by dx, right? D by dx, d by dy, d by dz. Del dot b, d by dx, d by dy, d by dz. D by dt you did not see anywhere. So these are the Maxwell's equation for what? Static, electric and magnetic fields. So this is what we studied initially. D dot ds. What that was equals to? Q enclosed. This was equals to Q enclosed. This is known as integral form because you are doing the integration. This is known as point form. What was the point form? How would you remember? That's our okay. D dot ds, Q enclosed. So del dot d dv, rho v dv. So del dot d is equals to rho v. This is known as point form. Why point form? Because I told you divergence, curl and gradient. These are point operation. Not gradient, sorry. Divergence and curl are point operation. They are defined at a point. Basically, if I say del dot f at some point, del dot f at some point is 0. Del dot f at some point is negative. Del dot f at some point is positive. So these kind of things are there, no? So that's why they are known as point form. Because divergence and curl are defined at a point. Okay. So in the lecture of divergence and curl, I said this thing. So not important, but just if someone is having doubts that sir, why we call it point form. So this is why we call it point form. So del dot d is equals to rho v. What was your closed line integration of electric field? Electrostatic field. What was the closed line integration? 0. So del cross E is equals to 0. B dot ds equals to what? B dot ds, that is equals to 0. And from here what did you get to know? That my del dot b is equals to 0. Why is that so? Because whatever the field lines will go out, the same will come in. So that b dot ds is equals to 0. H dot dl, this is the only thing which I am asking you to remember. I enclosed. Okay. Although you need to remember two things, both are simple only. D dot ds is q enclosed, H dot dl is I enclosed. So from here what did you get to know? How will you remember it? H dot dl. Okay, sir. Del cross H ds. Now I in terms of ds, how I can write it? I in terms of ds. This is your del cross H, right? I in terms of ds, how I can write it? J dot ds. So del cross H is equals to, here I am writing Jc. So Jc is the conduction current density. Here I am removing the word volume. Okay. Because you would know that if a closed line is made, if there is a closed line, that means it is enclosing some surface. So certainly we are talking about conduction current density, conduction volume current density. If it is enclosing a surface, a closed line will always enclose some surface. So if this is the sign, then by default you would know that it is certainly your volume current density. Okay. Surface current density will be defined with respect to a open line, right? What do you see? What do you call it? Which kind of nature it is showing? So divergent nature it is showing. Divergent nature means basically Q will diverge it or minus Q will converge it. So divergence is not 0. This is what it is showing. Here curl is 0. Which nature it is showing? Conservative. Here divergence is 0. So which nature it is showing? Solenoidal. Here curl is something. Curl is not equal to 0. If curl is not equal to 0, that means it is showing circulatory nature. Circulatory nature. That means certainly it can frame a closed loop. And you can see that magnetic field always frame a closed loop. They are framing a closed loop. So it is showing the circulatory nature. They are showing circulatory in nature. What are the remarks? It is known as Gauss law. Gauss law for electrostats. And this is E dot dl is 0. So what do we call it? What all the remarks we can say? Conservative in nature we can say, or we can say irrotational. What do I write? I would write the same thing only. Electric fields are conservative in nature. Electrostatic fields are conservative in nature. Or anything else we can write. Irrotational thing we can write, but electric field lines are conservative. Or irrotational also I can write, right? Nature is irrotational. So here I am writing irrotational. The question is, what they will say is that this is they will make a table A, table B, and you need to match the following. So what they will write? Irrotational. So irrotational, that means electric field are irrotational. Del dot D is equals to del cross E is equals to 0. So that's why I am writing all these things. They will write divergent. Divergence means divergence of magnetic fields is 0. So divergence of electric field they must be talking about. So del dot D is equals to rho V, and that is equivalent to Gauss law. So that's why we are making this table. So that will help us to solve some MCQ problems. Solenoidal, or what it will show, that magnetic monopoles doesn't exist. And what it will show? Del cross S is equals to JC circulatory it is. So yeah, it is Ampere's law. This is your Ampere's law. So regarding this statement or regarding this statement, everything that can be coming is this circulatory or Ampere's law. Regarding this statement or regarding this equation, everything that can come is solenoidal magnetic pole doesn't exist. Regarding this equation or regarding this equation, whatever that can come is conservative irrotational electrostatic fields are conservative. So these all the things that can come. And regarding this equation and this equation, whatever that can come is divergent and Gauss law for electrostats. So this is the end of our first lecture. In this lecture, we have studied the Maxwell's equation for static electric field and magnetic field. So we have studied Maxwell equation for static fields. Okay. Now we will study about time varying fields. So in the next lecture, we are going to study about time varying fields. Okay. Thank you very much. And if you found it helpful, you can comment down. Thank you.